So I guess we can get started. So what is the goal today? Hopefully we can finish this topic. If not, there will be very minimal left for the next week. So next week we will be doing reviewing our past papers, but basically you should be able to expect everything to be done or largely done this class. If not, there may be just 1 or 2 minor issues left here. And I'll also release the very last assignment 6, which is just some calculation on ANOVA and regression. So basically that assignment, you basically use Excel to do the calculation. So shouldn't be taking long time because you just compute give you the data, you just compute ANOVA and just compute the regression. So if you have been in the class, you shouldn't spend more than half an hour to do it because just basically plug in the thing. So I would put the deadline of the assignment like next Thursday so that I can put the assignment, I can put the answer on before the exams, maybe Thursday noon, something like that, so that you can have time to do it. But shouldn't spend much time on this because it's just applying what you learn from Excel. Okay, so just running the ANOVA and just running the regression. So before we go ahead to finish the very last pieces of our course, so let me remind you what we are doing in the regression. Right, it's closely related to the idea of ANOVA, right? And if you remember ANOVA is simply what we do is compare group mean, right? Compare group means, right? In the other words, what you are probably doing is, say, you're looking at education levels and versus income, right? And what you're trying to look at maybe these are the education level, right, of high school. And you have some data on students who or people who graduate from, say, college, right, or university, right? And some people who graduate from master or Ph.D, right? So you can definitely see the income level, right? This is M.Phil of master, Ph.D, right? This is M.Phil of like college or university, right? And this is the M.Phil of high school. Obviously, the three mean are different, right? And sometimes you really can't really say much because these groups are nominal, right? You can't really have a measure. But in this particular idea here, education, although it's now it's grouped by different degree they got, but you can easily think this number of years in the school, right? In that case, this become a numerical variable instead of nominal, right? Number of years in school, right? Then you can easily think now this become a scatter plot, right? Before it's just some kind of you can imagine this is the box plot, right? It's a different box plot, but now we have a nice graph here. We can scatter plot and we try to fit a line to do it, and that is and we call this line as regression, right? That is the meaning of regression. And how we do regression in this class is we are saying that this is the variable we use to explain the income. So this is what sometimes we call explanatory variable, right? This is called explained variable. And That's why we care about what we care is the vertical distance, because this is how well your model perform, because the performance is the line and what is not performing is the vertical distance. So that's why you are minimizing the vertical distance. Okay, and we care about the square because this is the way to calculate. It's much easier because you involve saying square, right? That's why this is the D, right? And we are minimizing these DIs, right? By what? Choosing the slope, right? Which is called A, maybe other color. Maybe this is slope is called A, right? And the intercept is called B, right? So we're choosing A and B, which is choosing where should be the line so that to minimize the sum of square distance. This is called the least square method, right? This we call least square method. And this method has no statistics, right? That's just basically you're given a bunch of data, you try to fit the line. Okay. And this is regression, right? Just give a line. So, and how do we give the statistical model, right? It's same as what we do ANOVA here, right? So that is the graphical explanation, right? And how to do the model. When ANOVA, right? The model we have is each observation, xi, is coming from some unknown mu mean I plus epsilon I, right? So, and we are saying that this is 0, right? And the variance of this is a constant variance, right? And we also have each group is independent, so we have covariance of this is 0, right? So that is what we have. And when you do inference, we will assume further this is normal 0, right? We assume there's a bell, right? So that is the ANOVA model, right? The one-way ANOVA model, right? So this is ANOVA model, right? Each observation you get is based on the group mean which we want to know, mu I, right? And epsilon I are things that is not captured by the group mean, may be some characteristic that we it's called random term. Something is not, we don't know what it is, but has mean 0, right? Same variance is across different groups the same, right? So this ANOVA. And this is needed, right? And how we do this is trying to use different estimate of sigma square, right? That we do is we try to come up with different measure of this is based on MSE, right? And MSW, right? If MSW is too large, then we will say that we can reject the null hypothesis that the mu's are the same, right? So that is the mu i's are not equal, are equal, right? So that is the how we are working on this problem, ANOVA, right? Two-way ANOVA will be similar, right? But that would be the main goal of what we have done. So now we have regression, okay? That actually is the same model, but what we have now is instead of explain X, we explain Y, right? The model will be like this: alpha plus beta xi plus epsilon. Okay. You can imagine that this is actually the mu I, right? But now the mu I is not a constant by itself, is the mean is affected by X. Okay. The X, what you observe is the thing that lead to different mean of Y. Okay. So you can see the structure same, except that now we are saying that the mean mu r is not completely exogenous. The role is played by some x. Okay, so you can see the structure is the same because you remember the assumption behind regression, the same idea, right? The same thing, right? The same thing here, right? The same thing. Covariance epsilon I, epsilon j is 0, right? Because we say it's independent, right? Epsilon I. We will today we'll assume this is true, right? And again, you will want to know, because we want to say mu are equal, right? So in fact, we want to see the hypothesis when C is whether beta is 0. That is something we want to know, right? Is it beta is going to be affected by is 0? Is whether x has any meaning on y, right? Has any impact. And also we want to see if alpha is 0 as well sometime, right? That would be also, we want to care if actually the intercept is 0 as well. Okay, so that is the you can see the parallel structure of these two, right? And that's why we would say in this particular case, ANOVA is a special case of regression, right? Where x, if there are two groups, right? X is simply telling me which group, right? 0 or 1, right? And that is actually you will see. Okay. Any question before we proceed? Is there any question? So that is the main comparison you may want to look at compared to ANOVA and regression. Okay. So if no, then we just go directly, because I think so far we learned enough hypothesis testing and estimation, so everything will become very straightforward. So there's nothing new from the rest of the material, basically just applying what we have learned. If you go backwards regression, we study how they're related, okay? And mainly the scatter plot, we want to find the best fit line, right? And least squared method is minimizing the vertical square difference, so that is the main meaning, right? And we figure out what is the intercept and slope, okay? And one of the key things in these two lines is saying that when you try to best fit the curve, the line, what you see, the first one is saying that the line will pass through the center of data, okay? And that means that everything is being compared to the center of data, right? So that means that this explains why B is related covariance, right? Covariance is saying that if X is above the mean, Y is above the mean, right? So that's why you can basically, if a line, you can plot the center of data, you're passing through this point, right? So covariance positive means that it's more likely that data appear in these two regions, the blue region, than the red region, right? If blue is more than red, then we have positive covariance, right? So we have positive covariance, right? Covariance XY is positive, right? So that means that if you have more data in the blue than the red, then your line should be positively sloped, right? And passing through this point, right? So it must be passing through this point, right? So that's why the slope should be related to the covariance, right? Because if negative, then negative, right? And the next thing you would probably see is why you have the variance increase, then you would be having a less B, right? The reason is because the line must passing through the center, right? And suppose you keep the mean of X, right? You increase the variance, so everything just rotate along from red to blue, right? Because everything just shift right, because Y doesn't change. You just magnify the scale, right? So everything just more separate from X bar, right? So we do not increase the mean, but we just increase the variance, right? So just basically holding the variance, all the data spread out more compared to X bar, right? If you're on the right of X bar, you go more right. If you're left X bar, you go more left. And it's clear that when you try to draw a line, the better fit line would be a more flatter, right? Right, because you keep the, remember how you increase the variance, you keep this guy same, right? Unchanged. There's no change to this, right? So X bar, X bar. So how can you increase the variance? It's just like this go here, this go there, right? So keep the mean the same. You go the one on the left, you go more left, the one on the right, you go more right. So then you keep the same thing, right? And you can easily see if I keep increasing, it will become a completely flattened line. So that's why it's inversely proportional. Okay. Of course, to validate it is to prove it, but we're not the math class, so that's why the proof is in the slide, but I'm not going to go over that. Okay. If you're interested in the proof, you can check out the video that at the back of the slides that contain a detailed discussion of how the proof is being done. Okay. And after that, we know the 4 assumptions we have, right? We just described that. One of the additional assumptions that we have compared to ANOVA is the assumption 2, because now we have X. Okay. The reason is X is non-random is because of math, to make the math easier to handle. And if not, then things will become much more complicated. So this is a classical way that we consider regression. And for your purpose, I think it's okay to keep this in your mind, but just really don't worry too much about it at the moment. If you really go to advanced class, then you'll become more serious. But for your applications, though, probably you can safely ignore them for the moment. But do notice that this is a very important assumption. If you really just want to know how they're correlated, it's not an issue. But if you want to interpret your result as causal interpretation, cause and effect, then you have to be very careful. Okay? But for the moment, for your purpose, I think you don't need to worry about it, because you don't know how to verify this point. And how do you solve this problem will be left to the advanced class. So we cannot talk too much in this class. So the main thing is what we call blue, which said if the data is generated in this way, right? And depend on what data you draw, you get different A and B, right? And you try to figure out what is alpha and beta, right? Because you want to discover the real relationship between the two, but you only get A and B, right? Every time run a regression, and every time run A and B is very different. So A and B are random variables, right? And they're estimators of alpha and beta, and turns out they are unbiased estimator and they're efficient. So they're a good way to estimate alpha and beta, because that is what we're interested in, right? If the data is generated this way, right? So we actually want to know what is alpha and beta, right? Say X is advertising expense and Y sales, right? You really want to know how advertising expense is going to change your sales, right? So that is, you want to discover what's alpha and beta. Okay. So A is the intercept and B is the slope, right? That means A is the value that when X is 0, right? That is the Y, the value when X is 0. And B will be if X increased by 1 and how much Y will increase, okay? And so last time we almost stopped here talking about the residuals, right? And as we've hinted, the residual is, we need it because first, we want to estimate sigma square, which is how the other factor, the error, is big or small, right? In some sense, sigma square is a measurement of how good your model is, right? If your sigma is large, then your model is fit less well, right? So that is the thing we want to study, okay? So how to measure it, last time we said is how we do it is to do the same is do the counterpart of the regression, right? You basically just really run the regression, get A and B, and you get the real data compared to your model. The difference between your predicted output, which is y hat, compared to what the data tells you is the residual, right? So basically, let me write down here, right? Basically, this is the residual. So this is data you have, right? This is X, this is Y, and your bunch of data here, okay? And you did run a regression, okay? This line, right? And if you still recall, right? This is A, right? How you get A is Y bar minus B of X bar. And what is B? The slope, okay? The slope is simply covariance of XY over variance of X, right? So that is the equation. You get it, right? And how do you calculate the residual? Is look at the vertical distance, okay? This is called now it's called E1, right? This is E2, and this is E3. Oh, sorry, I should have E4 and E5, okay, and so on and so forth. And first thing, I didn't actually prove it, but implicitly we said is E1 plus E2 up to En, that is 0, okay? Well, it shouldn't be surprise you because you should be fitting the line in the middle, right? So it shouldn't surprise you this whole, okay? And second, we try to estimate the sigma by S square, right? S square will be just sum of okay, put it this way. We just E1 square, E2 square up to En square over n minus 2, okay? And the reason why this is the variance is the sample variance, right? And the only thing that is new is basically yn over 2, okay? The reason is we have two variable we estimate. We estimate a parameter A and parameter B. Okay, this is B. Okay, we estimate two parameter there. So when we estimate two parameter, there's n minus 2, right? Remember ANOVA, right? The number of parameter will reduce by n minus k, right? Because when you calculate it, this is basically MST, right? MSE, right? MSE. The MSE will be just n minus k, right? That is how we sorry, this is MST, not MSE, sorry. It's MST. MST here. The MST just the n minus how many number of group you are measuring, right? So now go back to here, okay? So that is the sample variance, and we often look at the textbook. They would call the square root of that is a standard error of estimate, or sometimes they call standard error of regression. Okay, depends on which textbook you use, but that is essentially means that based on the residual, you estimate the sigma square, okay, and they are the sample counterpart of the sigma square, right? The first one sigma square, the second one is sigma, okay, and you will imagine they will be useful for hypothesis testing. Okay, we will talk about it immediately. But before we go ahead, is there any question? I hope that is serve a good purpose of the review. Is it today? I think next week, right? No. No, I think it's wrong because I'm teaching the DSME. No, okay, I think it's a mistake. So, okay, any question? Now we are going to proceed to the next one. Okay. So the next one is trying to do the following. Okay. The goal of today is going to do 3 different tests. Okay. First, we will check whether alpha is 0 or not. Okay. We want to see the intercept is 0 or not. Okay. This is the first test we want to do. Called the t-test, but we'll go into detail one by one. The second is we want to see whether the slope is going to be following the also 0 or not. So this is second test. Okay. And we'll do ANOVA in this context. Okay. And what ANOVA is going to do is the same idea. We're going to test whether beta is 0, and turn out to be this F test will actually give you the same as T. Okay. And probably later you ask why we do this. This is just showing you that ANOVA still can be useful, and it has no particular meaning when we have only simple linear regression. When you have multiple regression, then the F test and the T test will be different. But we just keep it here. The reason why we would want to introduce this is because it will lead us to what we call the how fit is your model R-square. Okay, but let's delay it until we're done. So lastly, we will talk about how do we use this model, right? So after we show that the alpha and beta, but the beta is not 0, we want to use our model, right? The model is going to use X to predict Y, okay? And we try to look at what we call the interval estimate from the line, okay? So that will be the goal of today, okay? So then we'll do some Excel. If not this week, then we'll be next one. But so don't worry, we'll do one by one, and we'll do quickly because we almost learned everything there. Okay, we just need to apply what we learned. Okay, and first, I'm not going to do the proof. Will be skipped. Okay, but we can show, because A is a random variable, right? The intercept. We can actually show it based on our calculation. What is the variance of A? You can check if you want to know the detail. You can check the slides, the technical part. So this would be the variance of A. Okay, and you do notice that there are several things that determine what's the variance of A. Okay, it's asking how likely the intercept looks like, right? And obviously, there are several things. Look one by one. First, if you have bigger sigma, the intercept will have much more variation, which is normal, I guess. All right. And second, I think it's simple here is you have larger n, then the variation is smaller. So I don't think there's any issue here. Okay. So the first thing probably would be is this guy. Right. This is something. Maybe you're concerned or not, but this is looking at in absolute term how X are, right? That means that if X are very big, the variance is very big, right? So you can imagine the following. Okay, you try to compare two situations. Okay. Here I have one data set, one of the other data set. Okay. And in case one, the data is like this. Okay, the data is mainly located in here. Another case, the data is located here. Okay. And remember, you're just collecting some of this data and plot a graph, right? So it's likely that what kind of slope you can get. If you get something above, you will get this slope, right? If you get something below, you will get something like this, right? Depends on what data you get, right? Maybe somewhere here or there, depends on what data you got. Okay. And if you if you do the data here, okay, sometimes you may get this. Okay. And sometimes you get this. Okay. And if you're unlucky, sometimes you may get this as well, right? And you're lucky, you can sometimes get this as well, right? Depends on what kind of data you got. So you can easily see that if you X is much larger, right? The intercept right here will be very small, but here can be very big, right? So that's why the intercepts can change a lot. If the data is further away from 0, right? So that explains why we have the above, right? So that's explain. This is we have explained. This is explained that this one, okay. And last one, if you want to explain this one, this is asking how each data are different from the mean, right? And if all the data are closer to the mean, right, that means that your data is actually can be drawn. If it's closer, right, then your data will, this variance will get smaller, the variance get higher. What does that mean? Okay, let's compare two different cases. See why we make your variance larger. Okay, so let's compare two different cases. Okay. Again, and we have X bar here, X bar here. Okay, X bar here, X bar here. Now we are saying that the data have one has less variance, one has more little variance. Okay, suppose this is a very little variance like this. The data is like this. Okay, the population data looks like this way. Okay. Okay. And now another case, the data is like this way. It's much higher, right? So what kind of line you can draw in here? In this one, okay, you might be getting the line like this. Okay, and similar, you get this one, right? And you may also get the line. If you are lucky, you get this too. You get like this, right? And if you're lucky, you get something like this, right? If you're unlucky in this dimension, you may get this guy, right? But you're this or this one, right? So you can see the variation, right? If this concentrated on this one, the variation of A will be large. This variation of A will be small. Can you see that? So that is the reason why the variation of intercept depends on how X looks like. Is that clear? So I hope that gives you the, although we don't really prove it, I hope I give you the idea why they are right, because that is the important point, right? Because the math properly, there's no one would challenge this math because it has been there every textbook. So I don't see you will have problem, and the proof is already in the slide, right? Although we just don't go over it, but it's not very difficult to prove, but it's there. So I hope I convince you that this is the right formula, right? And what we do extra is, if the random term are following the bell, A is also a bell, which probably not surprising, right? Because A turned out to be a regress. The key here is X are non-random, right? Remember, X are non-random, okay? So A is just a linear function of Y. So linear function of epsilon, right? So that is why A is also a bell, right? So that is the reason A is a bell, okay? And it's unbiased, so that's why we have mean of alpha, right? So what does that mean here is what we have is alpha. So A has the center of alpha is a bell shape, okay? And what we're doing with a bell curve, center is alpha, right? We want to test this alpha is 0 or not. Just simple t-test. Remember what we learned, right? We have a variable which is normal. We want to see the mean is 0 or not. Just simple t-test, right? Is that clear? So we have know how to do it, right? So we take the square root of this guy, right? How to do it? You replace this one, right, by the s, right? This is the estimate, right? And everything goes on, right? Take the square root. Is that okay? So that is how. Is that okay for this one? Any question? So that is how actually you conduct a t-test, because we know how to do it, right? So basically you want to see if more than 0, less than 0, right? You just subtract from 0, but you just don't write that, right? That's over the standard error, okay? Probably the only thing that might little bit require some energy or require some distinction is this n-2. In general, it's n-1, right? But in this model, as I said, you estimate two things. So that's why you n-2 here, okay? And this in general, that's how you count the degree of freedom, okay? And the proof we omit, but that is the only difference, right? It's a normal, right? Because let me repeat the statement here is because this is normal. Oh, okay. And alpha is also normal. Okay. With a complicated object there. Right? So that everything what we learn from hypothesizing continue to hold. So there's nothing new to learn here. Right? Everything same. Of course, the proof we omitted, many things we omit, but and the key is how actually you prove this guy, okay, will be a very complicated mathematical reasoning behind, and that is if you learn statistics in math department or stat department, that will be what they spend maybe a few classes to learn it, okay? But we are not, we just apply what they learn, so that's it, that's easy. Right? Just basically use this technique. Okay. And of course, if you go further, what you learn, right? What distinguishes probably, right? You will say what is data scientist, right? Or data engineer, right? Is whether and data science is to apply this formula, right? And data engineer and data, then they will know how you get this kind of formula there. So, but anyway, since we're B school, so that's okay. Okay. And after you do hypothesis testing, right? If you know this is not 0, then you can go ahead to consider the point estimate, right? The point estimate, I guess there's nothing new, but because A is unbiased, right? So that is what we get, what we want to do, right? And we know this the margin of error, right? Is defined as in this one, right? P critical value times the denominator, right? And the CI will be just like this, right? So this is nothing new, but what we have learned. Is that okay? I think there's nothing new from this context, right? Because we know a normal, we know how to do everything, right? So everything is very straightforward. I mean, it's good to have example so that you would know what's going on, okay? And after this example, I'm trying to show you the Excel. You can do it. All this calculation need not be done. Everything will be come up with Excel automatically, okay? I'll just show you this slide and then I'll show you Excel to do it and then have a break, okay? And if you remember how last class we did that, right? And then we, remember how we did it? This is A plus BXI, right? And in this example, A is 3.9, B is 0.07, right? You can plug in, you calculate the YI hat, right? And E will be just to remind you, this is Y. It's just YI minus YI hat. So just make sure that you know every single element where it comes about, right? And just to remind you how you get A and B, I think you know it, right? I don't think you need to too much worry about it. I mean, in case you don't know, you just basically you can use the intercept function in the Excel, right? Intercept, right? You can also use the slope function in Excel to calculate it. Okay. Of course, you can go to the basic formula to get those. Now, we also saw that in the previous example, we show how to get S, right? S will be just, you take square of each number there, right? And over n minus 2, which is 3, right? And take a square root, you get S, okay? Next is we want to calculate the variance of A, right? Or standard error, right? Or standard deviation, the estimated. So remember, the variance of A is what? It's just sigma square over n fraction, sum of xi square and sum of xi minus x bar square, okay? And first is this part is being done, right? And n is actually, 5, okay? And we need to know this guy and this guy. And this guy, sum of this is 55, is 1 square plus 2 square plus 3 square plus 4 square plus 5 square, which is 55. All right? This is just 1 square plus 2 square plus 3 square plus 4 square plus 5 square, right? Because x are 1 up to 5. Okay. And this SXX is each number minus the mean, right? And x bar is 3, right? Remember x bar is 3, right? So this 1 minus 3 square, right? 2 minus 3 square, so on and so forth, right? Actually, we did it, it's 10, okay? So that's why this, right? You just plug in the number here, right? Give you 2.191, okay? And later we will see this one. I think this Excel function is called STEYX, okay? You can actually calculate this directly, okay? And the next part would be we just divide A, which is 3.9 here, divided by the ST, the standard deviation, standard error, right? And we get 1.79, okay? We get a T, then we just compare the critical values, okay? Or you use the p-value method, okay? And the critical value, because degree of freedom is 3, right? So it just basically is this, right? What you get, this number is 1.779. You want to know this area, and here we do 2 tail tests, right? So you want to see if this is area is less than or more than 2.5%, okay? Or you do the critical value, okay? And the critical value is like 3. so you cannot reject. Okay, so which means that you really can't reject it. Right? So it's not, the intercept basically means nothing because you cannot distinguish it from 0. Okay, but still you can do a confidence interval estimate, right? You can also 3.9, use this number 3.18 is here and put number there. Is that clear? Okay, don't worry. Now I will go to Excel and show you how I can do everything with output with a single button. Okay, so then everything will become very trivial. Okay, but you need to know how this different thing comes about. Is there a question before we go ahead? Okay, so if no, then I just go to the Excel. Let me clean up the writing. Don't worry, it will be, things become very easy because it's very relaxing because you know all the material already. Okay, that's basically how to apply it. Okay, let me quickly do this. Okay, so I have Y, I have X. Let me copy the data first. So you were doing something similar for your assignment, so don't worry. You can see it's not going to take you a long time. Okay. So this is data, okay? And probably you want to remind you again how to do the slope intercept, right? So there's a shortcut, right? Intercept and slope. Okay. The first thing we want to do is to get the regression result, right? And we don't need to start from scratch. We can basically just use the intercept. Okay. And you put what are the Y, okay, A2 to A6, and tell them the X, B2 to B6. Okay. So I will give you the formula here, right? The slope. Okay. And do the same for slope. Give the Y and give the X. Okay. And in case the Excel crash, let me save the file first because this computer easily crash for some reason, which is very mysterious. Okay. And the thing I want to show you, the first is the standard error. Actually, you can find. Okay, standard error. Okay, is you put the Y and put X. Okay, this is 2.8. Okay, and this is X should be the same as what we found out here, right? This is the S. Okay, so that makes our life easier, right? So this is the one way to do it. Of course, these all calculation you can done easily. So, but I'm not going to repeat this one. Rather, I'm going to show you STEYX. Besides that, I'll show you that you can use the Addin, can produce everything from one click. Okay. So what I'm going to do is I'm going to make a duplication of this spreadsheet. Okay. We will do a regression Addin. You will figure out that is so easy. Everything become simple. Okay, we don't need this anymore. So how to do this is go to data. Actually, it's not here, the analytics. So if you use the Mac, it's similar. Okay, but I only show you the window because it's only Windows system. And I repeatedly telling you that you go to work, still a lot of place still use Windows. Unfortunately, or fortunately, I don't know whether you like Mac or not. So here, Addin, I use go and choose analytic toolpath. Okay, I think we have done so many times already, so it shouldn't be any issue for you. So I go to data analysis, and here I will use the last thing we do is regression. Okay, data analysis and regression. Okay, and it will be very simple. Okay, and what you do is just tell them what is X, what is the Y. Okay, so Y would be just this column A, or I just highlight the A stuff, okay? I just do column A. And X is column B, okay? Or just B1 to B6 is fine. So here, there are several things to look at. Here is I have label in the first row, so I have label, okay? And converse level, you don't need to do it because unless you want to do other things, so it's already 5% default. So you basically put the label and you're almost done. Only thing is the output, where to put output, okay? I put output is D, okay? So it's done already. So you can see it's just a few clicks. Tell them what's Y, what's X, the data of label, tell them output, okay. Okay. Maybe they don't allow me to do it. This Y and X. Okay, that should be fine. Okay, so you can see this one contain this one we know this is STEXY, right? This is if you want to see, this is STEYX, right? You put this one, we just learned it, right? This is the standard error, right? So this is how we, okay, and we will learn this one and this one, okay, and we will not learn this two guy. It is to the green one. You will learn it when you go to advanced class, not this class, okay? These two green will only be relevant when I talk about more than one variable, okay? So it's not a concern for us. So only the yellow one we need to worry, okay? And after the break, I'll talk about this ANOVA, okay? But you will see what we have just done, just did is we have this intercept, right? This is this intercept, right? And this is 2.19 is here. Okay, this is the error here, right? This is 2.191. Okay, see SA. Okay, maybe you want to write this as SA, right? This is the t-intercept, right? So they basically just this over this, right? So basically this is this E17 divided by EG17, right? So just this coefficient over the standard error, right? Maybe I can show that to you in case you want to know. So this is just this over this. Okay. So how to calculate p-value here, right? The p-value here is just looking at the tail area, right? If you want to do it, it's just t this, okay, of this guy, right? And degree of freedom, you have 5 data point, -2 is 3, okay? It's cumulative, okay? But this area is the left-hand side area, okay? And you multiply by 2, okay? And 1 minus. Because you know it's on the right-hand side. The reason why 2, 1 minus is this, right? Remember, center is 0. Here is 1.77. You leave this area, right? But you calculate left area, right? Then you have to 1 minus, get the right area and multiply by 2 because that is the this equation. So that's why you get 17%. Okay. So I hope that become clear how you calculate this too. Okay. And here we have the confidence level 95%, right? -3 and 10. How it comes about is here, right? You need to calculate the critical value, multiply by the SD, right? The S, and you get the value. And you can see that this A0 is within these two numbers, right? So that means we can't reject the null, right? That is exactly what we expect. Okay. So I hope now everything become clear in this, at least for you know how to calculate the yellow one, right? I'll cover the rest after the break. Is there any question? If no, then a break of 10 minutes, and then in the meantime, I'll go around to answer, to see if you have any question. Is it better? So as I said, some of you have concern about the p-value, how to calculate in the exam. I cannot say too much about exam, at least for not this class, but what I'm trying to say is, if the p-value, you need a calculator or Excel to calculate, then it would not appear in the exam, right? If you are able to figure out the answer using the T table or the Z table, right? You don't need computer, then it can be appear exam, okay? But if that is we require computer to calculate, then it's not the goal of the exam, right? Similarly, if the question require a lot of computation, then you shouldn't expect those things would happen, right? Because our exam is 1 hour, so we're not expecting you to engage in a calculator competition, right? So I guess we're done with the A, okay? So the next part will be B, will be very similar. So I'm not going to talk too much, okay? But let us see how this thing looks like, okay? So variance of B, okay? Probably may not be surprising to you, is related to sigma square, right? The more the variation of data, right, the more B, right? So it just means the following, right? If you let me draw the picture. Right, so you can see why is there so much interference. Okay, so you can see if I try to draw this, right? If I have another graph, right? And I have the data here. I have for some X, I have the data is like this, right? Okay. And compared to other case, the data is like this. Okay. This is small sigma. There's large sigma, right? So if you try to draw the line, it is going to be right? The slope is going to be like this, maybe sometime can be look like this, right? So there's some variation, right? But you look at this one, the line can be this, can be this, depending on what you see, right? So the slope can really vary a lot, right? So that's why the larger the sigma, right? So much more variation in terms of the B's, right? I hope this can explain why you got this formula, right? And the same graph or a similar graph can see if X are more center, the B will be larger, right? Because the X is more center, some slight error will magnify a lot, right? Because just like we're similar to this idea, right? If the data is very center, then it can go very easily, right? Just actually we have the same actually the graph like this, right? So you can see the left hand side, right? This one have the feature that this is being small, right? And this is big, right? So you can see the slope is much larger on the left hand side than the right hand side, right? So that means the variance of B will be larger on the left hand side compared to the right hand side, right? So I hope I convince you, although I didn't prove it, but I try to justify why this is the right formula. And of course, the proof, we have to read it, but we don't have time to go for proof. So what we have again is if the random term, okay, is follow normal, B follow a normal, okay, is the variance. And why this? This is Gauss-Markov theorem, right? The expected is unbiased, okay, unbiased. Remember this, unbiased. B, okay, B is unbiased estimate of beta, okay. And you never know this guy, so you replace it by S, right? And that's it, okay, and take a square root, okay. This is SB. Is that clear? Is that okay? So once you have this, then normal, right? We know the variance that's going to do the T, right? Normal, and then we just the same thing happen. Right? Everything would just progress as usual. We want to test beta is 0 or not. We just subtract from 0 divided by that, and -2, the same thing. Everything goes on the same. And this is the standard point estimate. This is the margin error. So I'm not going to go to every detail here, okay? And I guess everything is pretty straightforward, okay? And could highlight, right? This is the variance is this guy, right? Over the square root of 10, right? So that is, maybe I used another color, right? That is how you calculate the S of B, right? You take the B over the S of B, right? Give you this T statistics, and then it's less than the critical value, then you can't really reject it, right? And you can still do the confidence interval, right? So the key statistic is this number, 0.6, 1.96, and these two number here, okay? So this number here, number here, they all appear in our Addin, right? So you can try to check the Excel, right? All the numbers are here, okay? So let's go to the Excel. So 0.7, we know how to do it, the slope, right? Okay. And standard error, we know how to do that, right? As well. It just the standard error of the regression over the sum of the SXX, right? So this is we know how to calculate this too, right? And this guy we know how to calculate as well, right? So this is just the column E over column F, give you the column G, right? And use the T table, right? The T distribution, 2 times 1 minus this guy, right? Of the T will give you this number, right? And use critical value, you can calculate all this yellow thing, okay? Because the stop intercept is the same thing, I'm not going to repeat. And all the calculations already in the Excel, so in the slide, so I hope that should not be an issue for you. Is that okay? Is that a question? Should not be a question, you know every value there should know how to calculate. Is that a question? Is that a question how each number is being done? No? Anything? No? Then, okay. So here we come to almost the second last part to our class, ANOVA, okay? We do one way ANOVA, okay? And why is ANOVA there, okay? And the ANOVA here is trying to see, we analyze the variance, okay? So later you will see what actually we're doing, okay? The first one is looking at the SST, which is standard way we do. Just look at all the data Y, subtract its own mean and square, right? So this is exactly the way we do the ANOVA, right? You just subtract it from square, okay? And the next one we call SSR, okay? SSR is what? SSR is look at sum of square regression, okay? So looking at this is the line minus the mean, okay? So I think it's easy actually. I think the graph in the next slide would have it, but I think it's also good to draw it together with you so you see how this comes about, okay? So let me quickly draw the line, okay? Here we have X and Y, and we have line here, okay? And we have bunch of data, okay? Okay? So remember what we have is if we don't use anything about X, okay? How do you predict Y? You will use what's the best predictor? It's just the Y bar, right? Y bar is the model we should have if we don't have anything about X, right? If you don't know X, how can we predict Y? Just the Y bar, right? So what we want to explain is indeed how the Y bar different from the data, right? So this is what we call SST. Well, look at this distance. Every single distance is SST. Right, maybe I change a little bit this guy to make it. Okay, I just remove this. Okay, this is SST. Okay, of course, distance and square, right? The distance between each data and the mean of Y is the SST. Okay, and what is SSE? SSR. SSR is, this is Y hat. Okay, this is Y hat here. Okay, SSR is this guy. Okay, the fitted line over the Y bar. So that is the what? This is what regression give you. Okay. So what is the regression? The variation explain the regression. That's why they call sum of square regression. Okay. Or okay. And the last part is SSE. Okay. So this is y bar square. Okay. And this guy is sum of y hat, y minus y hat. Okay. And this is just y minus y bar. Okay. SST. Okay. So that difference is here. So by looking at this one, okay, you can easily see that SST should be, not surprisingly, equal to SSE plus SSR. Okay. This is the total variation, right, to be explained. Okay. Okay. And SSR is variation explained by regression. No, sorry for my writing. Right. And this is variation not explained. Okay. Because the data is y bar, right? You want to explain the purple part, okay? And your model explain the SSR, right? And the SSE is the part we don't explain, okay? So that allow us to say what we call an important measure called R-square. R-square is simply the part you have explained over the part you didn't, or you supposed to explain, which is less than 1 or 0. Okay. So R-square is what we call how good is your measurement. Okay. It's called goodness of fit. Okay. And this is the part that I highlight in the Excel. Let me show in Excel. Okay. That is the part that explained there. Okay. So in the Excel here, we have the R-square is 70%, 27%. So in this regression, the regression explains 20% of the variation. Okay. So I hope. Is it clear what we are looking at? Okay. Just to repeat the statement because it's important. The model that we can use without knowing this regression line is the horizontal line y bar. Okay. So this is the benchmark that we use even if we don't know about the model. We have no information about the model, y bar is the thing we do. Okay. So what regression tells us is the blue part, right? The blue part is the line tells us is additional explained part. Okay. That's why it's sum of square regression. Okay. And the part that the regression failed to explain is the orange part. Okay. If the line is so fit, then SSE will be 0, right? So how good the regression is fitting is just the blue part over the purple part. Is that clear? Okay. So it must be between 0 and 1. Okay. So if close to 1, there's a perfect fit. If 0, then it's the worst fit you can imagine. Okay. So that is the idea. So that is there any question? I think this graph tells us actually basically all the things we want to talk about almost. There's some technical thing, but that would be okay. So if there's no question, I go back to the slide. Okay. So this is the formula we just explained, right? Just this thing that is not explained by your model, right? This is your model output. This is the thing you want to guess the difference, right? And the first one is the thing you want to explain. The second one is the thing you explained it, right? The thing is unexplained, right? Is that clear? The three thing, okay? And not going to do any proof on this, but this is the graph I have set, right? Same graph as you can see. And I just argue, right? This R-square is the percentage of the variation explained by the model we just had. The name is called coefficient of determination. Okay, I don't know why they call it this way, but that is the name. Okay, just a name. But usually no one call this name. Everyone call it R-square. So you know what's R-square. Okay, this is called R-square because this is a square there. And probably you would wonder how this R-square related to, in our topic 1, what is correlation coefficient. Okay, turn out, probably not surprise you, this R-square is exactly the correlation coefficient square. Okay, so sometimes that's why these people would write this small r. Okay, and this small R-square is the big R-square. Okay, and that's it. We basically close everything. What we learned, right, is the one we learned in the covariance correlation, right? Remember COR, right? It's covariance xy over the square root of variance x and variance y. Okay, so that is the covariance. Okay, R-square. Is that okay? Now, I want to take you to the Excel a little bit because there's a function introduced. This R-square is there already, right? But I want to show you that it's another function that called R-square. R-square. You can also do that. It's called R-square. Okay. Also, you can just create by looking at the y and all the x. Okay. So this also gives you the same result. Okay. So just to highlight that, without going into the Addin, you can also do R-square. Okay. So that's the only thing. But just a side note, because you always go to this one, right? So you just always go to Addin. So any question? Okay. Any question? If no, here just trying to show you how you can calculate R-square. Okay. I think at this moment, I think you're able to understand it, but I just go over quickly. Okay. This one, y hat, I think you know how to do it, right? It's just 3.9 plus 0.7 xi. This gives you this one. And you subtract hat minus I, gives you this column. And you subtract from the mean, you get the other column. And you subtract this, and you get this column, right? And you take all the square, right? And some of them, right, will give you the this one will give the SST, right? And this one will give you maybe the order I should change this SSE, and this one will give you SSR. Or maybe I should change the order because it doesn't look very nicely aligned. Okay, and that's how you would calculate R-square. Okay, but we show how to do it, and you can show you this correlation coefficient square is R-square. Okay, maybe I just quickly demonstrate this in our Excel. I guess that would be, I think it's quick enough. We can do it. Okay, so here I can do the CORR. Okay, which is CORREL. Okay, and we have y, and we have x. Okay, and we can do the COR square, okay, which is this guy square. Oh, sorry. Okay, so exactly as what we expect. Okay, so I guess now I don't see you have any problem for the R square. Okay, is there any question? So basically, what we come up with is the measurement of how fit the model, right? So we just how to evaluate the model. So first we understand whether alpha is 0, whether beta is 0, R square is how good the model is fitting, right? And also sigma is looking at how variation, right? So we almost have everything, okay? And here I want to say about the MSR and MSE, okay? Because we just use why MSR is 1, because we just have only one group here, okay, which is we use the X to explain, so that's why it's 1, okay? And this N over 2, I think, is rather clear, okay? So probably you would ask why this ANOVA, right? But this is same as one-way ANOVA. We use one grouping, okay, X, okay, to explain the Y, okay? So basically it's just using same as ANOVA, right? Because remember, the beginning, we draw the similarity of ANOVA and regression, right? Here we just basically using V group in ANOVA, right? But in our case, we just basically talking about whether the grouping is whether you have X without X, right? So you compare the case only have one scenario. So that's why there's 1 here, okay? The degree freedom is 1. Okay. And the degree freedom of this is n minus 2. This is same as what we've done with the one-way ANOVA. Okay, so we have done about it. So here actually we are comparing variance. Okay, and the idea is the following. Maybe I go to the graph. It's easy. So here we're trying to see the beta is 0 or not. Okay, the idea is very simple, right? We look at the measurement of variance measured by SSR and SSE, right? If the variance of SSR is big enough, right, then the slope cannot be 0, right? Because if it's flat, SSR, SSE should be looking at the same variance, right? But if beta is not 0, right, have some slope, SSR should be big. Is that clear? So you compare two variants, measured it differently, right? If beta is not different from 0, then in fact, right, the SSR should explain something, right? If beta is not 0, your SSR should be non-trivial, right? So that's why you're doing a variance comparison, comparing the variance measured by SSR compared to SSE. Is that clear? So that's why it's F-test, okay? Because you're comparing variance measured by two different ways, right? If actually the data is actually flat, then the Y bars and the Y hat should be the same thing, right? Because it's supposed to be 0, that is explained by the SS. So that's the main thing why we have, why you do a one tail test, okay? It's because the measurement of the SSR, all right? If beta is 0, actually these two should not be different from each other, right? Because that thing explains to not explain anything, right? Right? Because if you explain things, then it's much larger. Is that clear? Okay, that is and I hope it's clear. You can see why it's a white tail, because you can explain a lot, right? The MSR should be very big, right? If you can't explain, the MSR should be MSE should be similar size. Is that clear? Is that okay? And because you use only one beta, so it's 1. Okay. So I guess the F test is similar to the thing we do. Okay. I would draw your attention, because the same procedure, I'm not going to do it, but I want to draw attention to this graph, this ANOVA table, because this is usually the thing you look at the output, right? This is the one that you actually do it, and I hope you know how to handle it, right? So by construction, right? This is SSR, right? And this is SSE, and this is SST, right? I hope that is you should be able to see that, right? And this divided by this will give you 4.9, and this divided by this will give you 4.3. I hope this is also very clear to you, right? And just to remind you, in regression, this is always 1, right? And what's this guy? This is just n minus 2 in our scenario, right? N is 5, if you remember, 5 observation. So 5 minus 2 is 3. And the F is being this over this, right? It's 1.112. Okay. And you can do the p-value, right? This is same as we do ANOVA. In case you don't, we will just F this, right? And you put this value, okay? And this is the degree of freedom 1, and this is 3, and then true, okay? Do note that this is the value of the left-hand side, so it does 1 subtract. Okay, so that's how you get this. Okay. I hope, I don't know whether you can see it, but that's a formula. Maybe this formula. Okay. So I hope that is clear how we do the F test. Okay. And everything same as we do ANOVA. Okay. Same as ANOVA, because exactly the same thing. So I don't see the reason to keep repeating. All right, because you just compare these two, right? Look at F and look at the table. I think we do enough questions, so it shouldn't be an issue for you. Is that okay? Any question? It's okay? Is there any question? So maybe I go to the very last thing we want to cover in our class. Okay. Probably we will review a little bit next class, but that is almost the end of it. Okay. So that is rather simple. I don't think you would be too much worry. Okay. Here is I have a regression, right? The regression line gives us A plus BX. Okay, this is the line. So what we are doing is, suppose I give you a value called X0. Okay. And what is our prediction of Y, right? Will be just this number, right? This is our prediction of what the Y on average should be, right? Of course, Y can be anything, but on average, Y lies on here, right? And the variance of this will be just variance of this guy, right? And we're not going to show it, but this is just this guy plus this number. Okay? And I think it shouldn't surprise you. We have this guy, right? Because the higher the variance, the higher number of the variation, right? And you got more sample, this one gets smaller. Okay. And similarly, this one is if data are concentrated on the center of X, this one get bigger. Okay. So one thing I want to highlight is here. If your prediction, want to predict, is further away from your mean of your data, your accuracy get much smaller. So that's why the variance is larger. Right? If your data, let me quickly, your data is here, okay? If you're far away, okay, then the variance is much higher. Okay? So to do this, let me get 1 more minute, okay? I'm done. So you replace this by S. This will be your SD, okay? And this is basically done because this last slide, right, this is our point estimate, right? And we have our interval estimate, right? And this is our CI, right? This is our prediction, is the point there, right? Basically what it is probably I will talk again a little bit more about next class, is his X0 is here. This is our prediction, right? And it tells you what is the confidence interval, okay? What's the interval for our prediction, okay? And that's marked the end of our whole course. Of course, little bit rushed at the end, but I will do it again on next Tuesday, because Thursday is no class because of graduate ceremony. But we'll little bit go back a little bit more on this point as a review next class. We'll do a little bit review next class, and we'll go over the last year exam paper. Okay. Of course, we do Q&A as well. So I put the assignment there, but basically just run the Excel. Okay. So shouldn't be an issue anyway. Okay. So I'm sorry for a little bit rush here, but I guess shouldn't be an issue because all the things we have covered already. We just applying those. But in case you have a problem, we can go ask again next class. Okay. I'm sorry for 2-minute extension, but I hope you have a nice day. I'll see you next week.